Hey guys, I'm going to run through 4.6 and 4.7. For 4.6, it's talking about linearization, which is the process of using a tangent line to approximate a value of the function. So essentially what it means is, say that you have some sort of curve or something. I'm just going to make a random curve like that. Terrible curve, but whatever. So say that we have a tangent line at a specific point. So say that we have a tangent line here. I know it doesn't look like it's tangent, but just follow, just for the sake of the visual example here. Say that we have this tangent line. So say that the AP exam, or I don't know, question only gives you a value of slope here, only gives you a point, and it only gives you slope. Well, we know that with that information, that's the only information we need to find a tangent line right here. So assuming that we have only a point and the slope of the curve, we make a tangent line. What we can do with that tangent line is we can approximate values of the curve to close values around that point right here. So let's say that we take a point on the curve here, or a point on the curve, or sorry, a point on the tangent line here, or here, or here, or here, or anywhere that is close to the point that we have of the function f. Well, this point right here can be used to approximate the curve. Any of these points right here can be used to approximate the curve, and any point along the tangent line can be used to approximate values of the curve. But the further you go away from the point, so say you had, if you were to use the tangent line further away from the point that they give us, then the approximation becomes less accurate. But if we use points very, very close to the point that they give us and we plug that into our tangent line, we can approximate values of the curve using the tangent line. And that's essentially the idea of linearization. So let f be a function such that each point xy on the graph of f, the slope is given here. So this is called a differential equation right here, but we're probably not even going to use it for this problem anyways. The graph of f passes through the point 1, 2. So look, we know the point and we know the slope. So we know the point, we know the slope, so we could put this point right here into this differential equation, get the slope, and we can make a tangent line. Okay, I don't think we have to do that for this problem, but that's what we would do. The curve is also concave down on the interval from 1 to 1.5. So k is the approximation for f of 1.2. What this means is that k represents the value that we plug into the function. So I shouldn't have erased that terrible thing that I drew. Here we go. So say that we have, let's use this as an example. I don't really know what if this is what the curve looks like, but it actually kind of looks like it might fit pretty okay. But let's say that here is the point 1, 2. So this is the point 1, 2. All right. Now what we're plugging into the function is 1.2, but we don't have any function to plug it into, so we plug it into the tangent line. So this point right here is 1.2. It's a value very close to x here, and then the y value would be, I don't know what the y, I guess maybe we do have to plug it in to find out. Okay, so let's go ahead and do this. So we need a tangent line. We have a point. We need the slope. If you remember, the tangent line is y minus y1 equal to m times by x minus x1. And this right here is always going to be f prime, or the slope, or dy dx at the given point. And so we're going to plug these values right here to find m, right? And so we're going to get m is equal to 2 squared minus 1, so that's going to be equal to 3. So our line is y is equal to 3 times by x minus 1 plus 2. So here is our tangent line that we have. We don't have the function, but what we're trying to figure out is an approximation, and k is the value of the approximation, which comes by plugging in 1.2 into, not the function because we don't have it, but plugging it into our tangent line. So we got y is equal to 3 times by 1.2 minus 1 plus 2. So then we get y is equal to 3 times by 0.2, which is 1/5, and then plus 2, so we get equal to 3/5 plus 2, which is 2.6. So 2.6 is our approximation. And is it an overestimate or an underestimate? So actually this image isn't bad. So we have a concave down curve, which means it should have a shape that looks like an upside down parabola. An upside down, So on the interval from 1 to whatever value they gave us, 1.5. So this means right here that the tangent line sits above the curve, which means the value that we're approximating, which is 1.2, 5.6, it's an overestimate. So it's an overestimate, not an underestimate. Had the curve been concave up, like probably what you see here, where it has an upside shaped parabola, then tangent lines on this interval sit below the curve. And that would mean that it would be an underestimate. But yeah. Okay, so for 2, let f be a function such that each point xy on the graph of f is given by, so we have a slope here. The graph of f passes through the point 1, -2, and it's concave up. Let k be the approximation for f of 1.3. So it's a similar problem. I guess we're just allowed to use a calculator on this one. All right, cool. So I'm going to find m first. So m is going to be equal to 1/2 times by 1. So I'm plugging in this point into here to get the slope. So 1/2 times by 1 minus 1/4 times by -2 squared. So that's 1/2 minus, I think that just becomes 1. So that's going to become -1/2. So our tangent line, y is going to be equal to, or I could say y plus 2. So I'm just using x1 and y1 here, equal to our slope times by x minus 1. And it looks like we're trying to approximate the function at 1.3. So we're going to plug 1.3 into our tangent line to approximate it. So we get y is equal to -1/2 times by 1.3 minus 1 minus 2. So we get y is equal to -1/2. Now that's 0.3, so that's going to be 3/10 minus 2. So that's going to be equal to -3/20 minus 2. So -2 and 3, I think that comes out to be, I'm going to say that's going to come out to be -2.15 rather than -2.65. So, and is it an overestimate or an underestimate? So the curve is concave up on the interval. So in that case right here, that means tangent lines are going to sit below the curve, which means it's going to be an underestimate. So C. All right, select values of the derivative of the function of g are given in the table. So we have values of g prime. It is known that g of 4 is equal to 12. So look, we have a point. The point that we're looking at on g is 412. And we do have the slope there. So g prime of 4 is 2.2. So I could say m is equal to 2.2. What is the approximation for g of 4.2 using the line tangent? So y minus 12 is going to be equal to 2.2 times by x minus 4. Oh, so they're not going to let us use a calculator on this one, but they're okay with it on 2. All right, sure. Y is going to be equal to 2.2. We're going to plug in 4.2 for our approximation. That's going to become 0.2, and then plus 12. I'm using a calculator. So we got 2.2 times by 0.2 plus 2. So I get 2. I get 12. That should be 12. I get 12.44. 4 looks like it's similar. So we have the point. So the point here is 3 and 17. We're using the tangent line to approximate the value of the function at 3.2. So we have y minus 17 is going to be equal to the slope at 3. Slope at 3 is negative 1.2, and then x minus 3. And we're plugging in 3.2 for our approximation. So I got negative 1.2 times by 3.2 minus 3 is going to be 0.2 again. And then we're going to add 17, and I've got 16.76. Okay. For 5, let g be a differentiable function such that g of 3 is equal to 2 and g prime of 3 is equal to negative 3/4. The graph of g is concave down on the interval from 2 to 4. Which of the following is true about the approximation of 2.6? So, we have our point right here, 3, 2, and we know the slope, so we can say that y minus 2 is equal to negative 3/4, and then x minus 3. We're trying to evaluate the function at 2.6, so that's what we plug into our tangent line. So we get negative 0.75, and we're going to multiply that by 2.6 minus 3, and then we're going to add 2, and I get that it's 2.3. So 2.3 is what g of 2.6 will approximately be. So 2.3 is what the value of the tangent line is, not the value of the function g, but of course we're using it to approximate it. And is it an overestimate or an underestimate? So it's concave down, so if the shape is parabola shaped downwards, tangent lines will sit above it, and so that's going to be an overestimate, so it's going to be C. And hey, why don't I let you guys do 6 for me? How about that? I think you guys, it's pretty much the same deal over and over, so pretty easy. All right, 4.7 is L'Hopital's rule. L'Hopital's rule is a very useful and powerful tool used for evaluating limits, but only if the value of the limit is an indeterminate form. And we have to be careful with how we show this on free response questions. We can't be lazy about it on free response questions. We can be lazy about it on multiple choice, but not on free response questions. So here's what we need to show if it's well, best thing to do with limits, honestly, again, the first thing that you should do is just plug it in. Now, this is where you can't be lazy. You can't just plug into this expression. You have to show this explicitly for free response questions. You have to show the limit as x approaches 2 of x minus 2, and you have to show the limit as x approaches 2 of x squared minus 4. We have to show these separately. So whenever we do this, we use substitution. We plug in 2, we get 2 minus 2, we get 0. And then if we plug in 2 here, we get 4 minus 4, which is equal to 0. So the numerator and the denominator, their limits are 0 and 0, which means we have an indeterminate form. And so now we can use L'Hopital's rule, which says that this limit, if we evaluate the limit and have an indeterminate form, then this limit is equal to the limit of the quotient of the derivatives. So not the quotient rule. So this is also kind of weird. We're going to take the derivative of the top and the derivative of the bottom, which we would never do for the derivative of a quotient, but we're not doing the derivative of the quotient. We're just trying to find the derivatives of the numerator and denominator. So the derivative of the top would be 1. The derivative of the bottom would be 2x. And we're going to evaluate this derivative we're going to evaluate this limit right here by substitution. And when we plug in 2 here, we get equal to 1/4. So that is L'Hopital's rule. It's very quick and powerful for indeterminate forms only. So for this next one right here, so again, we have the limit as x approaches 0. Let's evaluate the limit of the numerator. And that's going to be equal to sine of 0, which is equal to 0. And we'll evaluate the limit of the denominator, which is going to be 0. And I have an indeterminate form, which means I can use the limit as x approaches 0 of the derivatives of the top and bottom. So the derivative of the top will be 5 cosine of 5x over 1. And I can plug in 0, and I get 5 cosine of 0. Yep, and cosine of 0 is 1, so this is going to be equal to 5. All right, for 3, so we're going to show the limit as x approaches 2 of the square root of 2 plus x minus 2, which will be equal to the square root of 4 minus 2, which will be equal to 2 minus 2, which will be equal to 0. And the limit as x approaches 2 of x minus 2 is going to be equal to 2 minus 2, which is equal to 0. So we have an indeterminate form. So the limit as x approaches 2 of their derivatives. So the derivative of a square root function is 1 over 2 root x. And then the derivative of negative 2 will be 0, and then we'll divide it by the derivative of the bottom, but the derivative of the bottom is just 1. And so now I can just plug in 2, so I get 1 over 2 square root of 2 plus 2. That's going to be equal to 1 over 2 times the square root of 4, so it's going to be equal to 1 over 2 times 2, which is 1/4. The limit as x approaches 1 of the cube root of x minus 1 is equal to 1 minus 1, which is equal to 0. And the limit as x approaches 1 of 1 minus 1 is going to be equal to, x minus 1 is equal to 1 minus 1, which is equal to 0. And then we'll do the limit as x approaches 1. Now we have to take the derivative of this. So just remember that the cube root of x is x to the 1/3, and the derivative of that is going to be 1/3 x to the negative 2/3, and the derivative of negative 1 is 0. And then divided by the derivative of x minus 1, which is going to be 1. We can plug in 1. We're going to get 1/3 times by 1 to the negative 2/3. But 1 to the negative 2/3 is still 1, so we get 1/3. For 5, the limit as x approaches 0 of 1 minus cosine of x is equal to 1 minus cosine of 0, and cosine of 0 is 1, so that's 1 minus 1, that's equal to 0. Then we'll do the limit as x approaches 0 of x squared, which is equal to 0. So we'll do the limit of the derivatives, and the derivative of 1 is 0, derivative of cosine is negative sine, so this becomes negative sine of x over 2x, which is going to be equal to, whoops, don't forget the limit. The limit as x approaches 0 of sine of x. Now I have to be careful here because I'm going to get another indeterminate form of sine of x is equal to 0, and the limit as x approaches 0 of 2x is equal to 0. So we have to do it again. The limit as x approaches 0 of the derivative of sine, which is going to be cosine of x, over the derivative of 2x, which is 2. This is going to be equal to cosine of 0 over 2, and cosine of 0 is 1, so we get 1/2 as the value of our limit. Okay, so we'll do the limit as x approaches pi over 2 of 1 minus sine of x, which is equal to 1 minus sine of pi over 2, and sine of pi over 2 is 1, so this is equal to 0. Then we'll do the limit as x approaches pi over 2 of 1 plus cosine of 2x, which is equal to 1 plus cosine of pi, and cosine of pi is negative 1, so this becomes 0. So now we'll do the limit as x approaches pi over 2. Now when I take the derivatives of 1, that's going to be 0. The derivative of sine of x is cosine, so this becomes negative cosine of x over 2 negative 2 sine of x. That's the derivative of the bottom. So I'm assuming that we're going to get another indeterminate form. So we'll do the limit as x approaches pi over 2 of negative cosine of x, the numerator, and cosine of pi over 2 is 0. And the limit as x approaches pi over 2 of negative 2 sine of x, and hold up. Do I get another indeterminate form now? So the limit as x approaches pi over 2, cosine of pi over 2 is definitely 0. When I take the derivative, I forgot the tool right there. There we go. That should still be 2x right there. So that's still 2x. So going back here, so we got so negative 2 sine of 2x, which is equal to negative 2 times by, now when I plug in pi over 2, I get pi, and sine of pi is 0. So I get 0. So one more time for L'Hopital's rule. The limit as x approaches pi over 2, the derivative for negative cosine is positive sine of x, I think. And the derivative of sine is cosine. So this is going to be negative 4 though. Excuse me. Negative 4 cosine of 2x. So I get sine of pi over 2 over negative 4 cosine of, now when I plug in pi over 2, I'll just get pi. And so sine of pi over 2 is 1 over negative 4 cosine of pi. Cosine of pi, so this becomes negative 4, so negative 1/4. Okay, 6 more. So we got the limit as x approaches 0 of cosine of x minus 1. And so we'll do the limit as x approaches 0 of cosine of x minus 1. Cosine of 0 is 1, so we get 1 minus 1, which is equal to 0. Limit as x approaches 0 of e to the x minus 1. E to the 0 is 1 minus 0 minus 1, which is going to be 1 minus 1, which is going to be equal to 0. So use L'Hopital's rule, the limit as x approaches 0, and the derivative of sine is negative sine of x over the derivative of e to the x is e to the x minus 1. And then I think we're going to need L'Hopital's rule again, so let's check. The limit as x approaches 0 of negative sine of x is going to be 0. And the limit as x approaches 0 of e to the x minus 1 is 1 minus 1. If we plug in 0, because e to the 0 is 1, so we get 0. So we have to use L'Hopital's rule again. Derivative of negative sine is negative cosine of x over e to the x, and that's it right there. So now plug in 0. The limit as x, we plug in 0, and we get negative 1, because cosine of 0 is 1, and then so negative 1 is the solution. All right, I know this is getting really annoying doing the limit of the top and the bottom, but it's important that you do that because that's how they want free-response questions. They want you to justify the use of L'Hopital's rule by doing this. So limit as x approaches 2 of x squared minus 4x plus 4 is going to be equal to 4 minus 8 plus 4, which is indeed going to be equal to 0. Here's the good thing. If you just know that it's going to be equal to 0, honestly, you're good to just say that it's going to be equal to 0. So x to the third minus 2x plus 16. So I'm lazy and I don't want to plug in 2, honestly. Or I guess I could plug in 2, but then I don't want to add and subtract. So I can plug in 2 and I get I get 8 minus 24 plus 16. That's going to be equal to 0. And that's honestly through, yes, I know if I add those together, it's going to be 0, but also based off of assumption, because I know I'm using L'Hopital's rule, and I know I can only use L'Hopital's rule if it's 0 on the top and the bottom. So maybe just like skip straight to it if you're pretty confident that you are going to use L'Hopital's rule. Limit as x approaches 2, we'll do the derivatives. So we got 2x minus 4 over 3x squared minus 12. And that's going to be equal to, I think we're going to need another, plug in 2. Yeah, because if I plug in 2, so the limit as x approaches 2 of 2x minus 4 is going to be 0. And the limit as x approaches 2 of 3x squared minus 12, that's also going to be 0, so we have to use L'Hopital's rule again. So the limit as x approaches 2 is going to be equal to 2 over 6x, and that's going to be equal to 2 over 6 times 2, which is going to be equal to 1/6. All right, for 9. Okay, so we've got some cosecants and cotangents in here. Okay, the limit as x approaches pi. So the limit as x approaches pi of cosecant of x. I'll be honest, I don't expect people to really know this, but if you do remember the graph of cosecant of x, I'll just use Desmos to illustrate this right here. Maybe, yep. So we'll do cosecant of x. So here's cosecant of x, and we're evaluating the limit at pi. So I'm going to draw a tangent line, or not a tangent line, a vertical asymptote at pi. So you can see that we have an asymptote on the left and on the right. So the limit as x approaches pi is definitely going to be positive. Oh man, I guess we might have to evaluate limits from left and from the right. Here, I'm just going to say this, positive, negative, infinity. I'm just going to be lazy about this, not going to lie. One side is positive, one side is negative, infinity, depending on if you're evaluating it from the left or from the right. You might need to be more specific on an exam, but I'll let it fly on the homework. And then the limit as x approaches pi of 1 plus cotangent of x. Cotangent of x will be similar. So let's go in here. And I don't think it matters if it's 1 plus. So cotangent of x. Yeah, if you do plus 1, that's just a shift up or down, which doesn't move anything. And then at x equals pi. So you can see the same thing from, if you're evaluating it from the left side, it goes to negative infinity. If you evaluate the limit at pi from the right side, it goes to positive infinity. So we get positive, negative infinity, which is an indeterminate form. And so in that case, we can do the L'Hopital's rule. So we have the limit as x approaches pi. The derivative of cosecant is negative cosecant of x times by cotangent of x. And then the derivative of 1 is 0. The derivative of tangent is negative cosecant squared of x. And then we can actually cancel out one of those. So then we get the limit as x approaches pi. And the positives cancel out, so then we'll get cotangent of x over cosecant of x. Okay, and here comes the trig. Cotangent is cosine of x over cotangent of x, and cosecant is 1 over secant. No, sine, 1 over sine of x. What am I thinking? Cotangent is cosine over sine. Yeah, there we go, sine of x. All right, so then don't forget that limit. So the limit as x approaches pi. So we get the limit as x approaches pi of cosine of x over sine of x times by sine of x. So keep change flip. So those cancel. So we get the limit as x approaches pi of cosine of x, and cosine of pi is -1. Oof, there we go. All right, I think this one will be very, very similar. So we have the limit as x approaches pi over 2. So if you were to graph secant, so even if we do 1 plus secant, not going to matter, secant of x, and then we have x is equal to pi divided by 2. You can see from the left and from the right side is positive or negative infinity. Okay. So the limit as x approaches pi over 2 of 1 plus secant of x is equal to, it's either going to be positive or negative infinity, and the limit as x approaches pi over 2 of tangent of x, I think we know what it's going to be. It's going to be positive or negative infinity. So an indeterminate form, which means we can use L'Hopital's rule. And so the derivative of secant is secant of x times by tangent of x. Over the derivative of tangent is secant squared of x. So one of those can cancel out. So then we get tangent, we get the limit as x approaches pi over 2 of tangent of x over secant of x, which is equal to the limit as x approaches pi over 2 of sine of x over cosine of x over 1 over cosine of x. So we get the limit as x approaches pi over 2 of sine of x over cosine of x times by cosine of x. Those cancel. So we get the limit as x approaches pi over 2 of sine of x, and sine of pi over 2 is 1. There you go. Okay, we'll do the limit as x approaches infinity of the natural log of x plus 1. So that's going to be infinity because the natural log of x, natural logs are increasing functions. So that, and even if it's slow, it doesn't really matter. So natural log of x plus 1. So as we go to infinity, it is an increasing function, even if it is a very, very slow increasing function. Nonetheless, it is an increasing function. At infinity, it will be infinity. So this is going to be infinity, and the limit as x approaches infinity of log base 2 of x, still infinity. So we can use L'Hopital's rule. The derivative of the natural log of x is 1 over x plus 1 over the derivative of log base 2 is going to be 1 over x times by the natural log of 2, if I remember my derivative of logs correctly. So that's going to be equal to the limit as x approaches infinity of 1 over x plus 1 times by x times by the natural log of 2. And if you evaluate, so this is still a ratio function, or rational expression rather. This is x times by the natural log of 2 over x plus 1. If you evaluate the limit of the top and the bottom, oh my gosh, so we get the limit as x approaches infinity of x times the natural log of 2, that's still infinity. And then the limit as x approaches infinity of x plus 1 is also going to be equal to infinity, so we can use L'Hopital's rule again. So we get the limit as x approaches infinity. The derivative of x natural log of 2, because natural log of 2 is constant, we can just do the derivative of x, which is going to be 1 times the natural log of 2 over 1, which is just going to be the natural log of 2. Okay, cool, I guess. So for 12, the limit as x approaches infinity. So if we evaluate the limit as x approaches infinity of 5x squared minus 3x, that's going to be infinity. The limit as x approaches infinity of 7x squared plus 1 is still going to be infinity. Now, I'm going to be honest. I'm actually going to stop right here. We don't need to evaluate limits at all. We already know a better way to evaluate limits of polynomials, and if their degrees are the same. We learned this in chapter 1. If their degrees are the same, the limit at infinity is going to be equal to the ratio of their coefficients. This is going to be equal to 5/7. Boom. Now, you could definitely show that using L'Hopital's rule, but I already know that. Okay, and I can do this all in one video. Let's do it. So we have 1. This is the multiple choice. Now, multiple choice, I am not going to show so explicitly L'Hopital's rule because it's multiple choice. Let f be the function defined by this right here. Let g be a differentiable function with the derivative given here. It is known that the limit as x approaches infinity of g of x is infinity. Evaluate the limit as x approaches infinity of f over g. So basically what we can say here is the limit as x approaches infinity of f of x. Well, here's f of x. So this will be infinity. You can rewrite f of x as 3x plus 2 over e to the 3x. And the limit as x approaches infinity of this expression is definitely going to be infinity. And then at infinity, because e to the 3x has greater magnitude than 2, this will become 0. But overall, it just is infinity because of the 3x. So this is equal to infinity. Thus, we can use L'Hopital's rule. So we get the limit as x approaches infinity of the derivative of f of x, which is 3 minus 6e to the negative 3x over, and then we're given what g prime is. G prime is 4 plus 1 over x. And let's evaluate the limit here. So at infinity, this will become 0 for the same reason that this becomes 0. So this is just going to become 3 over, and at infinity, this will become 0 for the same exact reasons why these become 0, because the magnitude on the denominator is larger than the numerator. So at infinity, they'll become 0, so we get 3/4. All right, for 2, we have a very similar problem. And I wouldn't be surprised if the answer is, well, actually, I can't make any judgment, so we'll find out. So we're going to get, well, you can see that we know the limit of the denominator is infinity. Since it's the same exact type of problem as the one before, it'll also be infinity, so we can use L'Hopital's rule. So the limit as x approaches infinity of the derivative of f, which is 2 minus 15e to the negative 5x over 1 over x plus 4 cosine of 5 over x. So this was the derivative of g, which was given to us here. And then at infinity, it becomes 2 over, so this becomes 0. This becomes 0 right here, so then we get 4 cosine of 0, because this becomes 0 at infinity, and cosine of 0 is 1, so we get 2 over 4, which is equal to 1/2. All right, so we have more L'Hopital's rule. I'm not going to be so explicit about it. I'm just going to check. So at 0, that's 0. Natural log, so this will become 1. So 2 minus 1, so we get the natural log of 1. And the natural log of 1 is 0, so we get 0 over 0. So we can use L'Hopital's rule. So then we'll just use the limit as t approaches 0 of cosine of t over natural log of 2e to, the derivative of the natural log is 1 over x, so 1 over 2e to the t minus 1, and we have to multiply by the derivative of the inside, which would be 2e to the t. I'm just going to put that in the numerator, so 2e to the t. So this is the denominator, this is the numerator, so let's, maybe I'll just plug in 0 now. Well, let me get rid of the complex fraction. So it's keep cosine of t times by the reciprocal. So 2e to the t minus 1 over 2e to the t. If I plug in 0, I get cosine of 0, which is 1, times by 2 minus 1 over 2. So I'm going to get 1 over 2, I think. So I get 1/2. All right, cool. I think that's right. For 4, cosine of pi over 2 is 0. Pi over 2 times by 2 is pi. Pi minus pi is 0. So we have the limit as x approaches pi over 2. The derivative of cosine is negative sine, so that's going to be negative 3 sine of x over 2. The derivative of 2x is 2, and derivative of pi is 0. So then we can plug in 1/2, so we get negative 3 times by sine of pi over 2 over 2, and that's equal to negative 3 over 2. Yeah. For 5, if you plug in 0, sine of 0 is 0, plug in 0. Looks like we get 6 minus 2, which is 4. Minus 4 is 0. So we get the limit. As x approaches 0, the derivative of 6e to the 4x is 24e to the 4x minus 6e to the 3x over 2 cosine of 2x. If you plug in 0, we get 24 minus 6 over cosine of 0, so over 2. So we get 18 over 2, which is going to be equal to 9. And then I'm just going to jump straight to L'Hopital's rule since I know what it is. The limit as x approaches 0 of 1 plus pi, and the derivative of secant is the secant of x times by tangent of x over 2x. Plug in 0. We get 0 in the denominator. So I think we might have to use L'Hopital's rule again. Secant of 0. Tangent of 0 is definitely 0. Secant of... Now wait a minute. Hold up right here. Oh wait, that's why it's not working out. What the? I didn't mean, that's not 0 right there. It's pi. I was like, wait. So we can plug in pi. Sorry about that. So then we get 1 plus pi secant of pi times tangent of pi over 2 pi. Tangent of pi. Let's think about this. Pi is over here. So x has got to be equal to -1. Y has got to be equal to 0. The hypotenuse would be equal to 1. Tangent is always opposite 0 over -1. So it's 0. Tangent of pi is 0, which means all of this is 0, which means this is equal to 1 over 2 pi. So C. Okay, and that is everything for 4.6 and 4.7.